Okay, I have no clue, but I got my sound working. So, we have a failing test. Hold on. So it is video 142, it's Thursday, okay. So we have a failing test, and we need to try to rework some of that code so that, I want to see if I can get another failing test that, strips down the current situation and distills what's going on, if that makes sense. So I had like a save state file. I'm gonna use that right now. So if I do, I'm gonna look for that save state really quick. And I'm gonna guess that. Hold on. I am looking for something. Come on. God fucking damn it. Today might not be a good day here. Okay. So let's go open up to do 2021 0217 to get started here really quick. Just pop up, open everything that we need to look at. And I'm also going to make a note here. I'm going to pop this to-do message up at the top of my list of shortcuts and just say, you know, to-do simplify range mapping test. Okay, so we got a lot of stuff over here. Let's take our test code. So fragment shader common code, right? So fragcom. I'm gonna put that over here. And we know we have a current test that is failing on us. It's this right, so this is the specific test case that's like it is modeled after the exact scenario that's going on. Like, okay, let's just run this. Let's run this. And I don't know if we commented out the test or not. I believe we left it in. Yeah. So if we go look for that error message, right? It's going to come from here. I'm guessing this is specific test case number 3. Specific test case 4, huh? Okay, fair enough. So I like this test case because it mocks up the situation exactly. However, this case has a lot of different numbers in it where I can't like plot these numbers out. Like 0 to 511 is too much to like reason about on graph paper. So the idea is, can we distill this problem so that we can we distill this problem a little bit so that we can see it fail on a set of numbers that is kind of smaller, right? So so the first thing is we have kind of this range here, this range test here. Do we want to retrofit this? Could we retrofit this and say, you know, the first, we could make like 4 more tests. We can make another chunk of tests that uses a different range, right? Since this is the test case that we want, maybe we want to try to simplify it and see if we can get something going here, right? I don't feel like duplicating all this test runner code to do the same thing over again. I don't know. But right now, as it is, it's kind of straightforward. So it's like maybe it makes more sense to just duplicate the code, and just try again. Let's think about it. Right, because we could have a thing right here, like, if, you know, we're on the first chunk of tests, we do one thing. If we're on the second chunk of tests, etc. Alright, we could switch that up, right? But that just adds a lot of complexities that I don't know if I'm comfortable with. So, I think what we're going to do is we're going to just copy this. Right, test code is supposed to be redundant anyways. We're going to copy it, and this is SC4, right, specific test case 4. And we're going to change it to 5. So anywhere we see... Yeah, so we're just going to change specific test case 4 to SC5. At vid IID 0142. And the time is 6:06. Renamed to SC5. We need a simpler test that is written in the same manner as this test become before this test. Something Okay, so what we need to do is we need to create a series of tests just like this, but we want to do it in such a way that the range of numbers is small enough that we can graph it out on paper. Because right now we can't really graph this out on paper. It's kind of like, it's too intense. So we're going to take this, and we're just going to copy this. We're going to copy all this code, right? Copy. And within here, we're going to call this... you know, SC4. We're going to call this SC4. Say that the time is 07 and 32. Simpler version of SC5 that hopefully will fail when we Okay, so basically we want to try to solve the problem on graph paper by making a simpler, more distilled case. So what I'm thinking is we have these two things here, and what if we try to make this range a little bit smaller? Like, what if we try to keep this as like what if we try to do things in kind of simple quarters, right? So there's 2 here and 2 here. Maybe between that there's 2 and 2 more, right? So 1, 2, 3, 4, 5, 6, 7, 8, right? So if we try to make this 8, right, instead of 512, then we have something that we can more easily graph. So exact same diagram, but we just want to keep the ranges smaller. Now, we have this kind of huge range of things, right? This range here is supposed to be bigger than this range here, right? So if we're doing this, then we have 1, 2. So really, we're going to say that this is going to have to be 8. Or we could say this is 6 if we really wanted to, right? So 1, 2, 3, 4, and then 2 in the middle, and then, right, and then 6. So 0, 0, 6. Right, so just a distillation, right? So 1, 2, 3, 4, 5, 6, right? That's the idea. And that's relatively simple. Like, I don't know if we're actually going to catch anything with something like this, but the idea is that if we keep it kind of simple, we keep the range of numbers smaller, then hopefully we'll find out what's going on, right? So this is 6, so 0, 1, and then down here, instead of this 30, 31, it's going to be, you know, 5, and then 4, 4 and 5, right? And so we can change what that range of values is here. And then this is the diagonal values here, right? This is 8, so this is 0, and we're saying that the what coordinates from here map to these things here, right? So, so we want a whole bunch of pixels to map to over here, over here. So if we're doing this, we have to make sure everything kind of goes into itself evenly. So if there's like, I'm thinking, you know, each one of these might want to map to like 3 pixels each or something like that. So we have 6. And so that's like, you know, 1, 2, 3, 4, 5, and 6, right? We have enough for that. We could actually make some room here and stretch out this diagram just a little bit more, right? So that we can see that one-based kind of like number line there. And then change how we're doing this. So how about 1, 2, 3 pixels, 1, 2, 3 pixels for each, right? That would still be relatively distilled. I don't think this is going to work exactly because we want yeah. So I'll just paste that in the middle for a second. Let's see if we can just draw out the entire. Let's see if we can draw this out without any. Let's try to draw this diagram a little bit better. So in the middle here, we're not expecting it to map to any of this, right? So these middle cells, we're not expecting to map to these corners where we have 4 pixels here, 4 pixels here, 4 pixels here in the corner. And 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if we're going to do that, we're going to have 8. But I was thinking. That's a little bit complicated. That's a little bit more than I want. I do think that doing things in terms of thirds might expose the problem a little bit easier. Like, I think this is more of an edge case. Like, doing things in fourths, I don't know if that's going to work. But then we want to take this larger diagram right over here, and we want to say, you know, come on. So this right here is this is the texture, right? So this is the texture. Small texture region. Let's just call this, you know, small text I don't know, or small text. So it's a small texture region is the idea, right? This is a small texture region that we're going to sample from, right? So this is the destination, right? So this is the destination. And then over here, we're just going to make this sampling area bigger, right? So I'm thinking that, you know, every one of these, we could say, we could still do things in odd numbers. So we could say that every one of these is going to be 3 pixels. But we're already gonna, like, if this is 6, we're already gonna run out of room pretty quick. So, maybe we want to try something. We're gonna try the simplest thing that we think is gonna get us some type of result, right? So what I'm thinking is each one of these rendered as 2 pixels, right? Because we know that what we're rendering is currently getting chopped in half, right? What we're rendering is currently getting chopped in half. So could we observe that maybe by saying that, you know, we want to scan through here and we want 2 pixels sample from here, or a 4x4 or 2x2 section of pixels sample from here, 2x2 section of pixels sample from here, 2x2 pixels sample from here. Maybe we want to do that, right? So if we do that, if this is 6 pixels, then this needs to be 12 pixels, right? So this is we're trying to figure out the minimum possible scenario where we can make this error kind of show up, right? So this is what we're going to go with, 12 by 12. And that means that this region here, these numbers here, are the bounds for are the rectangular bounds for these areas right here, I believe. So right, 480 to 511. So so when we're looking at this, we got 0, we got 1, we got 2, and 3, right? So 0 to 3 inclusive here for this big rectangular area. And really it's, you know, 0 to 1, since we have enough rooms, but since we're using small numbers here, 0 to 1 and 2 to 3 right here, right? Diagonally. And then over here, it is, it's 12, so it is, down here, we're going to have 11, or 10 to 11, right? We're going to have 10 to 11, and then we're going to have to 9, so 8 to 9. 8 to 9. 8 to 9. Okay, so obviously the diagram is kind of meh right there. So we're going to have to... I don't know what we're going to do. We could just skew it like that. I don't know. Or we could say 9... 10, A to B, right? 10 to 11. 10 to 11. Right, so A dash B is 10 to 11. That might make it, that might work, right? So let's see if we can put these side to side, right? So, so I'm going to say A, B equals 10 to 11. Right? Make a little footnote of that, and then see if we can just kind of like put these side by side so that we can continue doing what we're doing, and just, I don't know, I just feel like it would be nice if we could just keep these diagrams right next to each other rather than how we were doing it. So let's see if we can... It's not too bad. So I'm thinking of moving this up 1, 2. 1, 2, yeah. Okay, cool. And then... I don't know. Let's not worry too much about this. Let's just get it working here. So the first thing we want to do here is make it a little bit more impervious to moving around, because I'm getting sick of having to shuffle this around and getting it to not be aligned anymore because of the tabs or whatever, or the lack of spaces. So let's kind of just throw this in here like this. And so now we have like another scenario where we're trying to map things, but it's hopefully we can get this to actually fail, right? We're actually trying to create another failing test that is simplifying the scenario that we're looking at here. So let's throw this in here, and if we're lucky, we might be able to condense this a little bit more. If we're not, well, oh well. Okay, that's a little bit condensed. That's a little bit... Those are some close quarters that I'm a little bit uncomfortable with. Can we maybe give that a little bit more breathing room over there? Okay. I think that's about as good as we're gonna get. So let's just roll with that. I think that's good to start with here. And so it's a simplified version of this image over here on Imgur. And let's just say, you know, at vid IID 0142, and the time is, let's do 23 to keep up with the conspiracy. Done drawing diagram. So we're done drawing the diagram here, right? So we've drawn this diagram, and we're ready to make this thing called SC4, right? So we change this to SC5. We're gonna call this SC4, and we're gonna change around the values that we're using here. But for now, let's just take all this, cut and paste it. Now I know that we could have changed around the test we already had to like save lines of code and spend less effort typing. But the thing is, to have these kind of different tests isolated we're gonna thank ourselves for that later, I think. So let's just go over here, find where SC4 is. Okay, SC4 we already removed, right? Because we renamed the SC4 to SC5, right? So we got specific test case 5. So, you know, at vid IID 0142, and the time is 0022 and 42 because we want to be cool. So we got this test case to fail, which is great, because it accurately mocks up what we are seeing in renderer, but now we want to okay, so basically, it's good that this test is failing, because it's mocking up the situation that's going wrong. But, we want something where we can, so SC4, we want something that's a little bit distilled. So we're going to call this SC4, and we're going to say, you know, at vid IID attempt to distill at true to renderer I'm gonna call this true to renderer test case. So we're gonna have to give these, we're gonna have to label these, right? So we're indexing these, which is fine, but I noticed that we're shuffling around the indexes that we're giving them. So we might want to, you know, give them little labels. At vid ID 0142, and the time is 25:50. So this is the test, and we're attempting to distill this case, right? So that's what's going on here. Let's see if we can kind of adjust to line everything up nicely. So yeah, so now that we have this kind of commentary, I mean, we have way too much commentary, but yeah, so we have this test case here, and we haven't actually changed any of the numbers, right? So we've figured out kind of the test case we want. Right, so we want this to be like 0 to 5, right? And we want this to be like, we want this to be like 0 to 11, right? So over here, right, we want this to be 0 to 5. Right, so we want this to be 0 to 5 because this is 6, right? This is 6. So we can keep like a little note of what this input range is. The input range is 6. And the output range, I don't know what the output range is yet. So it's 0 to 11, right? Right? And that makes it 12, right? So so the input range is 6 and the output range is 12. So we have a nice little diagram of how we're kind of setting up this function call. Okay. And now that we have this, what do we want to do next? I don't know. Well, 0 to 5 and 0 to 11, right? Which is the range here. 0 to 5, 0 to 11. So we gotta fill out this table. We gotta fill out these tables. That's gonna suck, but we'll have to, yeah, we gotta figure it out, though. So, looks like all you gotta do is fill out those tables and we're good, right? All the macros and stuff, they're all the same, right? In terms of the number of tests and the number of columns, all that stuff, right? We're just taking the previous test and just kind of simplifying it. So, if we go over this first rectangular region, on the source, right? So this is the source, this is the dest, we actually have it kind of backwards. But in this source location, we want to go over 0 to 1, right? So 0, 0, and then 1 inclusive, right? And we're expecting that everything maps to kind of the zeros, right? And then we're going to go to the next cell over here, and it's going to be, we're translating on the x. So it's still 0 to 1 in terms of the x's, but on the y's, we're going to do 2 to 3, right? And we're expecting, yeah, so let's just keep on doing that. So we know over here is the maximums. So this is, 2 to 3 and 1, 1. And this is the inverted case. So this is 2 and 0, right? And 2 and 0. No, that doesn't look quite correct, so let's kind of look at this. So not 2 and 0 and 2 and 0, but this 0 is a 1, right? So we got a 0 to 1 versus a 2 to 3. Okay, that wasn't as inverted as I thought. So we got this the top left corner is a selection area from 0, 0 to 1, 1. That's the diagonal selection area, all maps to, 0, 0. Then we're going to translate on the y. So these x's should be the same. X's are the same. And on the y, we're going to go 2 to 3, right? I got that totally wrong. We are translating to get to the next cell over, we're translating on the y. So the y is the thing that is going to go 0, 1, 2 to 3. Okay, cool. And so then after that, we do the same thing, but we translate on the x, right? So down here, right, to get this x, or actually, no, we translate on the y now. God damn it. Oh, I can't think. Okay. So first of all, let's just take all these test cases here, put them here. So this is over here. So we want to translate over on the x to get this cell here, right? So to do that, we got to change this to 2 and 3, right? Pretty simple. Okay, now to get over here, right, this is on the y, x, y, then we want to take the second thing and we want to translate this down. So instead of 0 and 1, we want 2 and 3, okay? So you can see how these are kind of opposites of each other over here. These, like, little things have been inverted. Okay, so then down here, right, we just want the highest values of everything. So this is 2, and this is 3, and that's going to give us that diagonal corner. Okay, excellent. So I made that a lot harder than it should have been. Okay, so now for these other cells, we have to translate over by 0, 1. So 0, 1, 2, 3, 4, 5. So we need, let's do the diagonal first, right? So let's nuke these numbers right here. And let's focus on the diagonal first, because these will be kind of hybrids of the diagonal case. Right? So the diagonal case is down here. And all we need to do is take these numbers and add a certain offset. So we have these diagonals here, and we want these diagonals here. So 0 becomes, we have to add 1, 2, 3, 4. Well, actually, hold on. Oh, we're talking about over here. My bad. This is the source. Sorry, this is the source. We really should put source first, destination second, so we're not confused here. Because we got source and dest, and then we're trying to diagram this out, but everything's topsy-turvy. So it might make more sense to paste this here, right? So that way we have source and dest in the correct order. Right? I think that makes more sense. Okay, so, over here, here's the source locations, right? 0 to 1 is this kind of like selection area here, and then 2 to 3 is the selection area here, right? So it looks like we already kind of labeled it 8 to 9, right? 8, 9, 10, 11, right? So we should just be able to take these numbers, and 0 and 1 are going to be 8 and 9, right? So let's do that. Let's just go paste this here. And anywhere we see a 0, that's going to be an 8. And then wherever we see a 1, that's going to be a 9. Okay. And then we have 2s. And we have 3s, right? And so that's going to be 10 and 11. Well, let's just do... well, let's try just 10 and 11, right? Let's not use any macros here. Let's call this 10. And this is 11. Okay, so now that we have that kind of inserted, let's steal this. And let's go down to here, right, where we kind of like, we're inserting this. Kind of go over here, paste it. Readjust it as necessary, so we want the ones place to line up there nicely, so that looks good. Okay. So now that we have that, I feel like we kind of screwed this up. So over here, these are the destination coordinates. The destination is 4 and 5, right? 4 and 5 here. So instead of 8 and 9, right? 8 and 9 is going to be 4 and 5, right? So this is 4, 4, 4, 4, and then 5s. 5, 5, 5, and 5, right? So the idea is that we have a range, right? We have a range of 2 pixels mapping to 1 coordinate, right? That's being sampled on the texture. A range of 2 pixels, 10, 11, 8 to 9, mapping to just 1 pixel, right? Everything's mapping to 1 pixel, right? So we're trying to kind of stretch and zoom into a texture, and this is how we're going to make that happen. Okay, so we have this. I'm fairly certain that that is correct. So the next case is we're just going to hybrid everything together, right? So if we want to go over to this block on the X, right? We'll move over on the X, then we want to steal the larger X's, right? So we want to steal the larger X's here. So that's what we're going to do. We're going to steal the larger X's and interlace them here. We're going to take these larger X's here. Okay. And then once we have those, the Y, we're still at the same Y, right? So we're in the top right. So the Y has not changed, right? So we're going to take the smaller Y's and paste them down here. So we're going to take the smaller Y's. Okay. So now we want to do the same thing over here, right? So this right here, this top left, or, sorry, bottom right, or bottom left. This is bottom left. So 0, 1, 2, this is the bottom left here. The Y is changing, but the X is not. The X is not changing. So we're going to take these smaller X's, right? So the smaller X's get dumped in here. Smaller X's get dumped here. All the smaller X's are getting dumped over here. And then we want to take the larger Y's, right? Because we're moving down on the Y. So let's steal these Y's. So we got to hope that, you know, we made these calculations correct, because otherwise we're interlacing things that are wrong, and then it's going to fail because we transcribed them properly, and then we'll have to fix the values. But we'll know. Like, if a test fails, we'll check the integrity of it. We'll check the math and see if we made a mistake when we filled out the test table, or if it's actually because we got the code to fail, right? So, so I think we got all the commas. Let's see. Oh, no, we don't got all the commas. We got some commas here. We got some commas here. Okay, so let's try again. Do we have all the commas we need? Alright, so yeah, we got all the commas. Cool. So now it's kind of the same damn code, right? It's the same code as before. Right? All this stuff. So make a note of, you know, when this fails, what the error message means. This is the first simplified version of the test. Let's do 23 to keep up with the conspiracies. So yeah, right, what we just wrote here, this is a simplified, this right here, this table here, and this diagram here, for this test, which this name may change, this is a simplified version, right here. This is a simplified version of this test down here, right? So, this test where you go over a 512 by 512 area and try to correctly sample pixels from this 32 by 32 area, right? And so we have a large range of values here, and we got this to fail, and we got it to fail in a way that actually matches the incorrect behavior we're seeing on screen in our shader. So I'm satisfied with this test, this IMGR getting closer test, right? But now we want to take this IMGR getting closer test, and right here, we're going to take a simplified version, right? Simplified IMGR getting closer test. IGC is IMGR getting closer test, right? So we can say, you know, IGC equals IMGR getting closer test, right? So we can make a note of what that means. And yeah, so now we're ready to kind of give that a roll. Ready to give that a roll and see if we can get it to fail. And we are actually hoping we can get it to fail and make sure that it's because the actual code is wrong and not because the test is wrong. And if we can get that to happen, then we're going to be much better, in a much better situation to fix the mapping algorithm to our specification. So let's do /AAC2020.sh, and let's kind of zoom in here so we can kind of see this a little bit better. Alright, so let's just hope that we don't have any syntax errors. I mean, we did a lot of code, so I'm actually surprised there's no syntax errors, but we kind of just, you know, cut and pasted, so that's not too surprising. And so, simplified IGC fail 2021. The test index is 0. We failed on the 0th test. Okay, so now the next thing to look at is, well, did we do everything correctly, right? So we're expecting 0, 0, and we're getting 2, 0, right? So let's look at that, because we might just have the test table wrong, right? Test index 0 would be this. And we're expecting to go from 0 to 1, right? So this is in the 0 to 1 range for the source. And we're expecting the output index to map to this kind of 0, 0. And instead, we're getting 2, 0. And nowhere do we want 2, 0. It should all map to this 0, 0, right? So we have this. Let's make sure we have this mapped out correctly, right? So we got 0 to 12, right? So we're expecting that. Is this all proportional, though? Do we screw our proportions here? Right? 1, 2, 3, 4. Right? 4? 4 times 3 is 12, right? So 1, 2, 3, 4 from here. These 4 pixels map to, sorry. 1, 2, 3, 4. These 4 pixels, or these 16 pixels. Let's do it on one dimension, right? So, on this dimension we have 1, 2, 3, 4 pixels on the x-axis are mapping to these 2 pixels, right? So 12 and 6 are divisible. This looks to me to be a simplification of what we're going after. I think that we actually got this working. I am kind of scared that it's not correct. So, right, let's draw something out. Let's draw some more stuff out, right? Let's look at this, right? So we have 0, 1, 2, 3, right? And then we have 4, 5, 6, 7, right? They have some space, and then we have, you know, 8. Okay. We got 9. And then we have 10. We're just going to make an A for 10, and then 11, right? So this right here is our 12 or 0, 12, right? Let's just put a 0. I know 0 is technically octal. But this is our 12 right here. This is our 12 range. And we're mapping down to the 6 range, right? So when we're mapping down to the 6 range, what we're hoping for here is this 0, 1. And then we have some space, right? We have some space, and then we have 1 and 2. And then we have some space, and then we have the 3 and the 4, right? So I kind of like drew that out so that we could see how it's supposed to map a little bit better. Right, this is 6. So this is the range 6. And so we're trying to sample from here. So we're trying to sample from right here, this range here. And we want it to map to here, right? So we want these two to map to these two. And then we want these two to map to these two. And then we want these two to map to here. But we don't... Hold on, got that wrong. We want these two to map to these two, but we're not testing that. We want these two to be mapping to these two. We're not testing that. We want these two to map to this one here. We want these two to map to here. Sorry, did I say these two? These 4 are mapping... So these 4 are mapping to these two, which these two should map to this pixel here, and these two should map to this pixel here, right? That is the expectation. That's what we're trying to go for. And I don't think that's what I'm seeing, right? So now that we have this kind of laid out a little bit better, we can look at this diagram and see if that makes sense. So let's describe it one more time for the camera. Oh, sorry, 0, 1, 4, 2, and the time is 47 and 23, to keep up with the conspiracy. Explaining range below. Okay, so we're going to explain the range below one more time. So you see this diagram here, this is done in like 2 dimensions, right? So the idea is we're going through like a very large canvas that represents the viewport, the screen, and we're trying to zoom into pixels on a texture, right? We're trying to display these pixels as bigger than they actually are, right? So we want to say this section of 2 by 2 pixels needs to map to this 1 pixel. This section of 2 by 2 pixels needs to map to this 1 pixel, right? And so we're mapping out the numbers on just one axis here to help us understand what's going on, right? So we have a block of 4 pixels that wants to map to here, and we have a block of 4 pixels that wants to map to here. So these are the screen coordinates, and they should map to these 2 pixels. And these screen coordinates should map to these 2 pixels. So, in other words, these 2 pixels map to this 1 pixel, these 2 pixels map to this 1 pixel. So that is the idea. And we're getting some failures here. So, let's try to so yeah, I guess we just gotta figure out what's up with that, right? So we have SX and SY. Let's just look at the... So the y-axis is looking correct. It's the x that's not working. So we got 1, and we're expecting it to map to 0, but it's mapping to 2. So this 1, we're expecting to map to 0. And it's instead it's mapping all the way over to 2, which is crazy, right? So we got to figure out how to fix that. And holy crap, that's like way off. That is way off. How are we gonna fix this? So let's think about the math, right? So we might just want to make another formula. Right, so let's close the OpenGL polyfills. I don't think we need this. Tau Depot, do we need this? Well, at the moment, we are considering looking at this because Tau Depot, when we're trying to figure out the texture pushes, this might be important, but right now, I don't think we need this. Okay. PAINT5D, do we need this? I don't think we're going to forget about PAINT5D. It's kind of the main system we've been working on for, how many times? We're on, like, this is the 73rd video working on PAINT5D. I don't think we're going to forget about that file. Tau depot data. This is where we were looking at this to make sure that we had the correct math for one of the test cases we were kind of plotting out, and we emulated that test case perfectly. Yeah, I'm not worried about this. We can close this for now. And, okay, yeah. So let's think about the math here. Let's think about what's going wrong and how we can fix it. So we have this input range, and we have a value on the input range, and we want to map it to the output range, right? And we want to do that correctly, right? And so somewhere we're kind of failing here. There's some offset calculations and things as well, but let's worry about just focusing on the input range, output range, and try to get that working correctly. Try to get a formula for that. And maybe even kind of like test out, like maybe run all these tests on, like run these tests twice, but the first time, instead of running this, we're gonna run it on something that doesn't account for that always zeroes out the range, right? Or something like that. I don't know. So the percentage calculations, I think, are not working very well. So we want to know, what do we want to know? We want to know, when we go from the input range to the output range, how many pixels are allocated to each one of these things, right? Because it all goes in evenly, right? So let's just say, you know, we have like, let's say zeroed out input, zeroed out input, and zeroed out output. Zoe and Zoo, I don't know. So we have input value. So we have an input value. Sorry, we have input values and input ranges, right? So this is input value. And so hold on. So the output values, and then here are the oh, I see what we did here. Right, so we have an input range and an input value, right? So we have to know what the range is, right? We have to know what the range is. And I think that the incorrect calculation of the range might be what is making our formula not correct. So let's create like a formula that kind of accounts for this, right? So let's say, you know, let's pretend that in fragcom, maybe we're going to make like a, we have this thing here. Maybe we make a helper function that this will use, and it's going to do a range and value. I'm going to do range and value, RV, range and value 0. So, I don't know. Range and value 0. Convert to right, so maybe like this, and then, you know, int32 r0, right, and int32 right, so range and value, and then int32 range 1, right, so and then return output value. Right, so we have something like this. And it's going to be like a int32. Alright, so it's going to take a... Is that kind of how we wrote this, right? So int32s and ivec2 out. Okay, so ivec2 out. Because... I see. Let's not do that. This is one axis. Right? X or Y axis. Input range, right? And then over here is, you know, X or Y axis. Input value. And then over here is the, you know, X or Y axis. And this is the output. The output range. Let's call this input so it matches. Okay. So I like the idea of that. So let's think about how this works, and let's try to test it out, right? So, this mapping. So let's make a note of this, right? So, this mapping is designed for mapping from large range of values to a smaller range of values. Okay. So we're gonna keep that kind of like idea where 1, 2, 3, 4, 1, 2, 3, 4. Okay, so we're almost there. But yeah, so let's so yeah, we'll keep this as like, yeah, this is how we'll write it, as mapping from a smaller range to a larger range. I don't know if it's actually going to work if it's the other way around, right? So, so we just want to assert that R1 is less than equal to R0, right? Alright, so the idea is that the input range is larger, the output range is smaller, right? Okay. So we just want to figure out what the cluster size is, right? So the cluster per output, right? So we just want to find out that ratio, right? So the clustering ratio. So So clusters equals, you know, R0, right, was the input range, divided by the input range. The input range is larger, right? So R0 divided by R1, right? Now this will kind of screw up on us if we're going from a 1, if the destination is a 1, 1, then if the destination is very small, actually no, if this input range is very small, well, let's not worry too much about that for now. So the number of clusters, right? So if we go from here to down to here, it's not quite that though, right? It's 2 of these go to 1 of here, right? And then 2 of these go to 1 to here, right? So we might want to create a different diagram that kind of exemplifies what's going on there, and say, right, and just remove some of these, and say, well, what if we were mapping like this: 0, 1, and 2, and that this range was 3, right? And if we do that, then we have, let's just try to line this up all nicely. All right. So if we're trying to go, let's keep this diagram. Let's not map. Let's forget about labeling that as a range. I think that we can already kind of know that one of these things is a range and the other thing is the values, right? I think that's kind of implied. And okay, so we got this nice little diagram kind of explaining kind of what we're doing. It's a little bit ugly because it's like taking up a little bit too much room, but it's going to help us figure things out, right? So clusters, this is a cluster. Is it are we calculating clusters or are we calculating cluster sizes? I think we're calculating cluster size, right? So, so I call it cluster size. So right here in the diagram, this is cluster size. And we're gonna have to make the variable a little bit smaller because we need to be able to put our notes in here, right? We need to be able to label the diagram, right? So, cluster size, right? Let's actually go put this where we're gonna put it, right? Let's go put it in this shader code here, right? So this is gonna be like a helper. This is potentially going to be a helper function that this code can use, right? So that's the idea. And we have to change the indentation a lot, though, huh? So we know these are inputs and outputs, so let's just get rid of that. And then we still have more to get rid of. So we got 1, 2, 3, 4. Okay, so that's okay. That's as compact as we're gonna get here. So yeah, this is the cluster size here, right? So if this is 3, right? The range here is 3, right? That's the output range. And the output range is always smaller, right? Because we're sampling from like a smaller texture. So 12 divided by 3 is 4, right? And the cluster size is 4. Excellent. So after we have the cluster size, what do we want to do next to figure out where we are? Well, we want to take this coordinate and we want to just divide by the cluster size, right? So destination pixel is going to equal the input value 0. Input value 0 is going to be divided by the cluster size. Right? So 0 cluster sizes equals 0. 1 out of cluster size is still, if it floor it. 3 out of cluster size, it still ends up over in this first tile here, right? And then once we're over here, right, we're on the next tile, right? So this is just basic tile math, right? So this kind of, yeah, it's just basic tile map grid math. I don't know why this was so hard to do. So that does mean that this needs to be floored, right? This needs to be floored. Technically, it should just floor out of the box, right? Because integer division should just floor itself. However, I don't know if GLSL is going to like how I'm doing this or not. But yeah, so so you got cluster size and you got the destination pixel. Okay, so cluster size, destination pixel, excellent. And it should be all we need for that output value, right? Yeah. I mean, we should just be able to, you know, and V1. Alright, so V1 and DP are kind of like synonymous with each other. It's the destination pixel. Yeah, I think that's all we gotta do, right? I think that's pretty simple math. I think that's all you have to do to get this kind of formula over here working. And so let's just make sure we can get this compiling. And if we can get this compiling, okay, so we got that compiling. We should make some tests for this thing here, right? So we're thinking that we could run all these tests on this, and we could try to get the same thing happening, right? that would be the goal, right? That for this, it would just run on this kind of thing and it would just work, right? So we want to like run all these tests multiple times and use this code on it and see if that gives us what we're looking for. Got ya. So the range is just inclusive, right? So I think we could do that. So yeah, let's try to retrofit this, right? So if so we have test index, and then we have I don't know what we want to call this. We got test index, and then we have but the output should be the same, right? The output should be the same. So let's just call it mega test group, because I don't know what to call it. If 1 equals mega test group, else if 2 equals mega test group, and we're just going to take what we have and in the second section, right now we're just gonna hit break for now. Well, actually no. Let's yeah, let's hit break here. To do. Or actually not break, but we want to continue. And this mega test group that we have here, we're going to wrap where we're going through all these tests. We're going to say, you know, for mega group equals 1, and then mega group or meta group is less than or equal to 2, and then mega group plus plus, right? Mega test group. And this one is test index. So we just do that, and then we just kind of loop through everything kind of twice, right? So I think that's the correct scope. Yeah. And what's in here? This is SX and SY, right? And this right here is next meta group and then test index, right? Okay. So then I know we call it mega test group, but let's say MG for meta group. And you can keep the commentary in there, right? Because I think that is nice. So MG. Going to be a mega test group or meta test group, whatever you want to think of it as. And then over here we just say, you know, int32 mg meta slash mega test group, right? That's what this is. Okay. So MG right here. Okay, so we're just expecting it still to compile, but we just want to see if we can. We still want it to fail in the same place. So we just want to jerry-rig this in so that we can see if we can get this this simpler formula to do our bidding, right? So we're also going to have to make a note that the you know, we're going to have to make a note of the meta group, right? We need to make sure that we know what meta group we're on, right? Because it should be 1, right? It should be the second set of tests is what's going to fail us, right? So we need to make sure that that meta group says what it is. And then after we can get this formula kind of working, I'm going to do some OpenSCAD code. So meta group is 2, right? Excellent, excellent. So now what we want to do is try to use this new function we wrote and see if we can get this to work, right? So we're going to try like this. We're going to try this function here. And we know that the range is going to be 5 minus 0. 5 minus 0, this, right? Plus 1, right? That's the range, the inclusive range. Okay. The value that we're using is going to be the SX, right? So, we're doing it on one axis first, so value in, right? The input value. And then we also want the output range. So range, I don't know if I like how I did that, but range value 0 to RV1, right? So I don't know if I like that. Range and value 0 to range and value 1. It's kind of written kind of weird. But the idea is to group it like this so that we know we have range and value. We have a range and we have a value on that range. Sure, we're just gonna... I know it's a little bit weird because I would like the two ranges to be right next to each other, but let's not worry about that. I think it's fine as it is. So 11 minus 0, 0 plus 1, right? Because it's an inclusive range, right? So because it's an inclusive range, we need to add that 1 to get it to be correct, right? Okay. Let's put some extra parentheses around here so everything kind of like looks a little bit more aligned. And this is the range out. Right, range out. Okay. And to get the, right, we're testing out the, if we look at the test case here, we're testing out dx in this thing here, right? So we want to do something like this. We want to say, you know, dst.x equals this thing, right? This formula here. Right, we're going to just break it apart component by component. And then dst.y, right? dst.y should equal this. And it's the same thing except this is sy, right? So it's the exact same stuff, but sy and sx, right? To get the dstx to dsty. Pretty simple, right? Pretty straightforward. And the goal is to never have this test fail, right? If we can run through all these tests and they all pass, and then we fail on this one, we know that maybe we can somehow integrate this code into the other code and then just get it working, right? So let's give that a shot, right? Let's give that a shot, see if we can get that to do our bidding. So I have some high hopes, but I don't know, man. We'll see. We'll see what happens. So we don't want it to fail on the first meta test index. So the assertion failed on line 137. So let's go look at 137. We're trying to assert that R1 is less than R0. So the output range. So we got this totally mixed up, didn't we? Because the range in is the bigger range, right? And we just screwed that up, right? We just screwed that up. We got that completely backwards. Right? Because SX is on that larger range, right? Yeah, source. And the source range is bigger than the output range. So we just got that, we just totally screwed that up, and our assertion kind of caught us there. So that's cool. But yes, this needs to be 11. Or actually, this needs to be 5. Sorry, this needs to be 5, and this needs to be 11, right? We just got to swap that. Right? So same thing here. This needs to be 11, and this needs to be 5. Right? Because there's 6 pixels here, right? So, and there's 12 pixels here in the range. That's why I have the plus 1s, right? So we're trying to write this in terms of, so that it kind of matches the case for the diagram here. Right? So we got 0 to 5 for a 6 range, and then for a 12 range, it's 0 to 11, right? So 0, 5, and 0, 11, right? Okay. So now that we have that, let's see if we can get this to work. Okay. Okay, so we're in some good standing because we have failed on meta test number 2, right? So right here, so let's make a note of here, you know, of what we're doing here. At vid IID, and we're at, where are we here? We're at 142, and the time is 1 hour, 23 minutes, and 23 seconds. See if this new one-axis version of function can output correct values. So yeah, we have this outputting the correct values, right? So now the next thing to do is, we have this thing here. The next thing we might want to do is, we have this thing, rec source to rec dest. It'd be nice to just create a new version of this that doesn't use this formula, and maybe it can map from so I don't know if we can map. I don't know if this logic maps from, if it'll work for larger to smaller. But let's kind of assume that this logic only works for mapping from a larger area to smaller area. I don't know if it works in the other way around, right? So so let's say this is going to be like IVEC2 AAC 2020 fragcom, and So we want to map from a bigger area to a smaller area, or larger to smaller. Big to little. I don't know what we want to call it. Sure, let's call it this, and then let's just give it all the same stuff, right? Let's give it the same exact signature. Do we want to name these something else though? So I'm gonna prefix these with big SX, and then let's just steal all this. Let's steal all this, right? And big maplet, and then we're going to change this source. We're going to call this big, right? The source is big, and the destination is smaller, right? So that's the idea. And I don't know how well this is going to work, but we got to try it, right? We got to just mess around and see what happens. Rectangle source, rectangle dest, right? So we got all these we got a lot of coordinates in here, right? But I want to expose exactly kind of like the range of values that we're using when we're mapping this, right? Okay, so to get this working, we should just be able to steal some of this stuff here, right? And take this. Alright, so this takes the function from above, and we just want to say, this is the big, right? So this is the x-axis, so it's big, SX1 minus big SX0, right? So we're taking the big range, the range input, right here. And then we're going to take the small, so small, which is going to be dx1, the larger minus small, or little dx0. Sorry, my bad. So little dx1 minus small dx1. We're going to take that SX range, so we're going to take the big SX, right? It's the big, right? So, big source value X, and this is, you know, big source value Y, right? So you got big and lit. Okay. And we add one to make sure that range is inclusive. And this is zeroed out, right? This is zeroed out. So after we create these, we want to say, you know, dst.x. We want to plus. We want to add the little range back on, right? So we kind of like took the big range and we zeroed it out with the little range. So now we want to like add that little range back on that we kind of zeroed out with, right? So if the little range is 0, we're not adding anything, right? But yeah, so dst.y equals, you know, dst.y plus, and we don't want to zero it out like that, though. We want to zero it out with the new range, right? So we want to do little destination x0, right? And then we want to do little destination y0, right? So so these two here are analogous to this here, right? Okay, yeah, so I think that's about right. So unzero out the output coordinate. All right, so the math. So no concept of offset in here. So there's no concept of offset inside these functions here, and that's why we need to make sure we do the correct offset removing calculations. So we'll just make a note that, hey, there's no 1, 2, 3, 4. There is no concept of offsetting in this section, right? So now that we have this kind of written out, this is going to be the big SY, so this is the y-axis. And all of this should be pretty much the same, right? So we want to take the big SY1, the big range value, and we want to zero it out. So big SY0, right? So we want to take that and we want to zero it out. And then this is just big SY, so that's fine. And then over here, we want to map it onto a new range that is also zeroed out. So we want lit destination y1, right, the bigger thing. And then we want to, you know, minus the little destination y0, the littler range. And then we also want to do a +1 because the range, if we want the correct range, it's an inclusive range, so we need that +1, right? So that would be the correct math for this. Okay. So now that we have that, we need to make sure everything kind of lines up, kind of like makes sense. So if we start color coding the X's and the Y's, we should see the blocks being completely analogous. That's right. So we've just color coded this and we see all the same matching colors here. Then we need to make sure that it makes sense over here. So X's and Y's, X's and Y's, X's and Y's, X's and Y's, X's and Y's. So we have X's and Y's for all the same categories, right? So these formulas are completely analogous. And so if we've gotten it right on the X, we've definitely gotten it right on the Y, right? That is the goal here. So map a value on one range to a value on another range. Written assuming the destination range is same size or smaller than the input range. Have no clue how this will work if that logic is flipped. So I have no clue how this is going to work if that logic is flipped. So and we'll say 32 because I like powers of 2. So yeah, we have a little function summary inside the function, right? So function summary. Actually, let's write it like a function summary. So that way we can look for tags that say function summary and we can find them later if we ever implement something like that. Okay, so yeah, we got this nice little function summary. Okay, cool. So I don't know if this is completely proper code, right? But now the idea is that maybe we can take this version of the function, right? This version, which is pretty much same signature as this, but we can insert that in here and see if maybe we can get this to work, right? So if 2 equals, you know, the meta group, or the meta test index, or mega test group, okay? Else, if 3, right? And then we'll just steal this, right? We'll say, you know, we can just literally steal, we can steal all this code, and we don't have to change one little thing, right? We can just, I mean, we have to change the function we're calling, right? So we have to change the function we're calling. But besides that, a rewrite of so here we're going to call a rewrite, right? So $42, because I like to be cool. So I'm going to hope that this version of the function is more correct, right? So we know that this case is failing here. We know that all of this is passing here. So the goal is, hey, maybe we can make this new intermediary function that correctly does all the logic, and then after that we might be able to figure out what was wrong with this function and rewrite that to make that function right. And then we have a little redundancy in our code where we have more than one function that does kind of the same thing. But let's not worry about that for right now. Let's just make sure that we go 1, 2, and 3 for that meta test group, right? The meta test group is going to go 1, 2, and 3, and depending on what happens there, 1, this is all passes. 2 was originally 2. This now we bumped it up to here, and we've inserted this. We hope that this will actually work out for us. So DST equals, right? So make sure that, right? So same exact signature. So we should just be able to pump it in with the exact same signature. Let's just put a little thing here, a little note here, so that we can find this. Right? So at same sigs. Right, so we can see that commentary and see, oh, at same sigs, oh, these two things have the same signature. Okay, so we might have to fix some syntax errors, but then I'm going to hope that good stuff happens here. Well, DST, undeclared. So we kind of forgot to declare, when we kind of like made this, we forgot that, you know, somewhere in here, then we called this rec DST, IVEC2. We just have to make an IVEC2 called DST. And DST is here. So output XY chord bar. So IVEC2 DST. Right, that's as simple as it needs to be. Okay. Now let's give that another shot. So once we get this working, or we get, once we can get this function working, I want to go to do some more open SCAD code, since I'm going to have to control reaches end of non-void function. So at some point when we did that, we kind of screwed ourselves over here. What did we do here? Oh, because we have to actually return this. Duh. Right, we have to actually return it, because this is not... Yeah, okay, got it. Okay. So let's just hope that this works out. Okay, so we got an assertion failure. on line 137. So we're expecting the output range, expecting the input range to be less than or equal to this range, right? And when we use this, it seems that we have made a mistake here where this range is somehow messed up. Actually, hold on. This is not the input range. Do I have input range and output range messed up here? I do. God damn it. The input range is the bigger thing, the output range is the smaller thing, right? God damn it. So everywhere I wrote this, this is completely incorrect. Okay. So that's... God damn it. This is the output range. Well, no, hold on. Just made a whole bunch of mistakes. So we screwed up this. We screwed this up. We screwed up this signature, didn't we? Right, so you can even see it here. 5 and 11, in and out. And then over here, somehow, we decided to be stupid and do the... what the hell? Okay, so let's go up here for a second. So we have screwed up the naming of our parameters. So let's go look at this for a second. Okay, so this has, you know, the input range is larger, right? That's not true, is it? No, the input range is larger. So this is wrong. Like, maybe the function actually works and we're just not mapping it correctly. Now I'm getting scared here. Source mapped to dest, right? The source range is the bigger thing, right? The source range is this bigger thing it's mapping to the smaller thing. So this range is wrong. Right, this range is wrong. This range is wrong. These ones up here are correct, right? So we have these ranges wrong. The input range and the output range have been messed up. So maybe the actual test code was actually incorrect. And that is scary. Right, because the input range is going over a larger set of values. Okay. Yeah, the input range is going over this larger set of values, and the output range is going over this, you know, smaller set of values, right? God. Well, that could drastically change some things for us. Okay, let's give it a run. That changes a lot. That changes... We're gonna have to reevaluate... We're gonna have to reevaluate the other tests that we looked at and see if those are even still correct, right? Because now, like, some of the tests we wrote might actually be... Some of the tests that we think are failing might actually be okay, and it's because we screwed up the range, right? So, right, so this is not... Right, this range here is... This is our 12. Right, it's a larger input range. And this is our 6. Right, this is our 6, and that's our 12. God damn it. Okay, well, let's just try to get this working. But yeah, some of our test code might be wrong. Some of the test code that comes after this might be incorrect. And then we'll have to... Well, we gotta reevaluate a lot of things now. Oh well. Okay, so... So this Imgur getting closer fail. Right, so we thought we could distill this test a bit and find something that, you know, would give us different results, but in the end, Imgur getting closer test is failing again. So now we actually got to look at that, because we might just have this test written wrong, right? Like the input range... Actually, no, the input range here is 0 to 511, the output range. So we got this correct, right? The input range is bigger than this range, right? And SX and SY, are they iterating over the correct things? Yeah, I mean, SX and SY seem to be iterating over the correct things. Okay, that's cool. Okay, so we still have this failing us again, huh? Okay, so now the goal here is that maybe if we... The goal here is now that maybe we can take the, maybe we can take the new version, the new function we wrote, and maybe we can just shove that in here, and maybe that new function is properly written. Maybe this new function, where we're going to take the big to little, big map little, right? Maybe that is properly written, and maybe that will pass all of our tests, right? So that's the hope, right? That then we map a big range to a little range, and we use this, that it'll just pass. It'll pass all the tests for this, and we'll be in a good place here. Yeah. So I do think we're gonna have a syntax error here. I think that... Oh, I expected that to actually have a syntax error. Oh no, over here we're gonna have a syntax error, right? Nope, we don't have a syntax error, huh? Okay, so let's go over here, and let's go U for just... So we're using the old kind of mapping logic. And so now the next question is... So this one just has some bad math, right? Okay. So let's go take this, which works, right? And then, let's go look for where we're calling this, right? So we're calling this from somewhere. So wherever we see this, we're just going to go into GPUView and look for that. Or we're gonna go look at the frag shader code for this. So let's go look up so where we see this, we're just gonna comment it out, and we're going to now we might have some type of like signedness things that need to be fixed, but let's just take this and pop this one in, right? So, and give that a roll and see if this breaks on us or if we can get this to work now. So, fingers crossed. Because this version of the function passed that one test, so I think we're going to be in good standing here. Okay, okay, so let's go U, and go... Bam! Bam, got it. Right over here seems to be a little bit off, maybe, but, right, there seems to be something that looks a little weird on the corners, but let's just snip this. And let's go to desktop. So it looks like we got it though. So let's close this. And let's open up the We Got It. So let's go look in let's go look at this and kind of zoom in here. Enhance and see what's going on here. Okay, so nope, so that was just looked weird because, you know, the pixels kind of look weird when you sometimes when you're trying to do things. But yeah, so this is pixel perfect, right? This is nice and pixel perfect. Everything is kind of lined up exactly. The tests pass for that. Right, pixel perfect. Okay, cool. So now the next thing is, where do we go wrong with our math, and do we wanna fix this, right? So why is this math wrong, and can we condense the formulas we've written and create the can we create a version of this that actually has the correct math? So we see one of the problems, I think, is doing this floating point logic, right? We're doing kind of these floating point percentages, and I think doing stuff in floating point is part of what's screwing us up. So let's try to make a version of this that this is not completely correct, though, right? It's not completely correct. But we have tests written for it. I don't know what we want to do with this. So let's, we could just not worry about it and move on, right? That's one thing. Actually, no, let's try to look at this code here. So, we got this thing here, right? And we call these functions. So, if we wanted to condense this logic into, like, mapping on one axis, could we make that happen, right? So, AAC 2020, fragcom, big X, big map lit. And it's going to be like IX. Let's call it big map lit with the capital X for x-axis. Let's just do that. Let's not make it too complicated. In32, actually no, X or Y axis. So this is going to be a one-axis version of right. It's going to be a one-axis version of that, right? That's what we're going to do. One ax equals one axis. Okay. So we can just call this source integer, in32 source 0, right? The lower, in32 source upper. And then we have, you know, in32 destination 0. And then we have, like, in32 destination 1, right? So we have source and destination coordinates. Okay. And if we use these, we want to take this kind of formula, right? So this formula here. So it's this formula. We have the big source coordinate. So source is the bigger coordinate, right? That was the idea. Big source, yeah. So this and this big S1. Here's S1 and S0. So those correspond to these. And then we got this 1. We got this 0, and we got this 1, and we got this 0, and we got this 1. And so D0, D1 is right here. And then this big SX whatever, right, because the S is the bigger, so SI, this is the input. So we got the range in, the value in, right? So we've kind of made a one-dimensional version of this. And I guess the first thing to do here is just test this, right? So say, you know, this is an int32. And then int32 di for destination out, and di equals this, right? So di destination output. So actually it's not di, it's going to be do, right? Do destination output. So we got in and out. So turn do. Okay, so before we even try to like undo this function and go into the guts of this and see what that actually needs to be, we have this big map little thing, right? Big map lit, and we're just gonna put the one-axis version. We're gonna just paste the one-axis version right here, and then we're just gonna make sure we can still compile. and then we'll write some tests for that as well. $156. Oh, we forgot our... Yeah. Okay. Alright, still working. Still getting the results I want. So now the question is, can we do this one-axis thing and write it into our tests? So, we know we have a thing in here called, like, meta MG for mega test group. And oh, this already works with else if 4 equals mg, then we're gonna try to do this thing again, right? Right, so this is going to be a refactor of this, right? That's the idea. Let's steal this. Put this in here. Right, this is the one-axis kind of thing. And take this here and just be like, paste that there, paste that there. And this is for 4. So let's go over here and change this to, instead of 3, it's 4. Make sure that everything still compiles and make sure that still passes, and then we'll kind of rewrite it. We'll rewrite it, and what we're going to do is we're going to try to, like, we have these multiple helper functions, that's all good, but we would like to simplify what we're doing here. Too few arguments, so, oh yeah, so this isn't quite the same, is it? Yeah, because we start off with the range, so we're going to start off with, like, this input range. Right, so we're going to have this input range, and then we're going to say, we're going to go from, you know, we're going to try 0, 0 to 11. And then we're going to try the same range. We're going to try the output range. We're going to go to 5. 0 to 5. Right. So the first thing we're kind of changing is that signature, right? We're kind of... It's the same thing for this other signature, it's just that instead of this being SX, this is going to be SY. So... input range low. This is input range high. And then over here, we have, you know, the output range. And they can steal that commentary and we can paste it over here. Okay, so now let's give that a run. Okay, so we kind of messed with our commas here and kind of screwed that up. So let's just do that so we can acknowledge we have a straight line of commas except for, you know, the first element. We can't have a lax comma before the first element. And let's see if that all passes, right? If that all passes, we're in some pretty good standing. Okay, cool. So now the next thing is just to go into this code here. And let's make sure that if we change this, to something else, like instead of 511, if we change this to like 500, or if we change this to like 1100. If we change this to 1100, we want to make sure this test actually fails if we change the values. Make sure that, you know, have a sanity check here and make sure that this is actually being, this code is actually being called, right? We want to make sure this code is actually being called, so we want to do a little sanity check, right? We want to make sure we're working on a solid foundation. So, okay, we are. The meta test index is 4. That's exactly where we made that change. Okay, I just want some sanity here because one of the worst things we could do is think that the tests are passing and then keep on working and be working on a shaky foundation. So, we're going to keep doing this. Okay, cool. So, okay, cool. So that passes. So now we can go into here and we can start to rewrite this a little bit more. So we can look at the code for this, right? And we see that that it's pretty simple. It's a pretty simple formula, right? All we got to do is figure out what CS and DP are, right? So let's go over here. And so we know right here that with this function, we're talking about R0. So R0 is right here, right? So we can just start cutting and pasting, right? So we can just take this and say, hey, this is R0, and we can just use some basic substitution, right? So anywhere we see R0, well, this is R0, we'll just paste that there, right? And so now we have R0. So this is R0. So that's R0, and then we divide it by R1, right? And that's cluster size. So R1, if we look at here, R0, R1 is this third parameter here. So this is R1. So we can make a note of that, right? We're dividing by R1. Right? R0. This is R1. And that gives us the cluster size, right? And we can substitute cluster size in here as well, right? Because it's only used in one place. So we can take this CS here, and we can just do this, right? You can put some parentheses around it and say, right, this is cluster size. Then we point to this bracket here, CS is cluster size. And then here we see that we have this formula here. So we can, we know that DP is destination pixel, right? So we can take this and say, okay, we got V0 divided by CS. And so here's CS. This is CS right here, right? So we can take this cluster size. We can paste it right in here, right? Because this is cluster size. And we see that we want to divide it by V0. V0 is the second parameter. And so we know this is the parameter, right? Or SI 0, sorry. V0 right here, V0 is, well, V0 is still just V0 here, right? So, right? Input. Right, so input value. So now we got a formula, and I'm noticing that we have +1s on this. These formulas seem to have +1s. So the math checks out that there needs to be a +1 on these ranges. It makes sense because the range it's an inclusive range. Also, if we have a +1 and a +1, we never have to worry about division by 0 errors. So we actually have a nice range mapping that won't lead us into a whole bunch of trouble. The other question is, does this work with just, and also this looks like it'll work with it not being floating point, right? We can just do this and it'll actually work, right? So return DP. Alright, so dust pixel. Input value. Okay, yeah, so we're pretty certain that that if we want this to work, that this is all we need, right? So I think that what we can do is we can take this and we can comment it out and we can put in this new formula that doesn't use any helper functions, where it's all done in the same place, so we don't have to pass around things between functions, right? So we get the cluster size. Right, cluster size is this. This is the input value. This is the destination pixel. And this is on just one axis, right? So let's go give that a run. Let's give that a run, make sure it still passes, right? If the test still passes, then that means that our refactor was successful, right? We've consolidated the logic. So let's go look at that. Oh, V0 is undeclared. V0 is the SI value. Right? So SI, right? So we have this, we got that, we got that, we got that. It's the SI value. My bad. And then we have the other values from the original things, right? So okay, let's give that a run. So I feel like I've written this formula exactly as it was before. And I'm not sure why I made the mistake to have that off by 1 error. Because this formula is a lot more elegant, right? We don't have to worry about division by 0 and the mapping just works, right? So that's, like, nice. Yeah, so that passes, right? That passes. We're able to use this. So now what we're assuming here is that we can take this one-axis version of the code and we can... Let's not do that. Let's just steal this, right? Let's steal all this. And let's go into the code that's actually broken, right? Let's go find that broken code and be like, hey, rec source, rec dest, this is all broken code. We can see, like, we have these ranges divided by these other ranges. So there's this range without a +1. And then if we look at this formula, right, so we're taking these ranges and we're dividing them, right? So we take the range and we divide them. It's not quite the same thing, is it? We have another division here. So we have a multiplication here. We've done it the other way around, honestly. We've turned that formula on its head, right? So instead of multiplication, so we have this range. This is the zeroed out range divided by the other zeroed out range. Or is it? We zeroed out the value and put it on the range, right? We zeroed out the value and put it on a range to get a percentage. Over here, we're taking the range. We're taking the range and dividing by the other range, aren't we? You're taking one range divided by the other range. So it is a different formula. It's a very different formula. It's not the same formula. So we're assuming, this formula is wrong. Possibly you could fix it by adding something to here, like doing a +1, but then we're just guessing and checking. And what I'd really like to do is just not guess and check, right? I would like to just say, you know what, this formula is wrong, but let's go over here and to our code that we're testing, right? Go look for this, right? We commented it out somewhere, I believe, right? Yeah, we commented this out because we were like, hey, this is the actual scenario. This is the actual scenario we're testing, right? This is the whole shebang. No, this is where we put it in the shader code, but where do we put it here? We commented it out, right? So there's some places where it's working fine. But then over here, we were just like, this is the actual situation. Yeah, this is the actual situation. So, let's do the same kind of meta index thing, right? So let's do the, int32 mg, this meta index. And then we'll do like the for mg equals 0. And then mg is less than or equal to 2. Let's do 1 to 2. Let's change that around. mg plus plus. And this is going to be 1 to 2. Then down here, it's going to be, it's going to be next, mg, and test index. Meta group, test index. Right, meta group and test index. And then that is actually, yeah, metagroup and test index. Then over here, it's going to be like next, SX and SY. And then we can kind of like line these up nicely. Okay. So now in here, right, we'll do this, right? We'll say, if 1 equals mg, then we do this, right? And then otherwise, else, if 2 equals mg, then we do this commented out function, right? Before we even put this back in, we just want to say continue. We just want to skip it for now. We just want to stub this logic in, and make sure we can get it working, make sure the test passes. Then we're going to try to stub this in, right? And we know this test is actually going to fail, right? We know this one's going to fail, but we're going to try to change the math. So So we're gonna throw the other test and the other code in the trash. So we're gonna say we're gonna take this function here, right? This function here, and I have a trash folder that I've been putting things in here. So file new, save this as we suck at math. Here is my original version of this function, right? And so we'll go into the documentation, and we have a trash folder and 002._, right? So you can take that full file path to the clipboard, and we can say fixed broken version in, you know, right? If you really want to know about that, you can go look in the trash, right? You can go search around in the trash, and you can see it's not really fixed yet. It's not fixed yet, but we're going to make this timestamp here. And let's make 42 because we want to be cool. So yeah, we're going to fix this. So we're going to, the first thing we're going to do is we're just going to start gutting it, right? So the first thing we want to do is we just want to say, screw all this logic. It's all wrong. So we might want to keep rec dest or whatever. No, let's just screw it. Let's I don't remember what this was. We'll keep that for now. Because I don't know what that was for. Let's go look in our hashtag comments and see if we can find commentary on that. Yeah, so we've attempted this formula multiple times. I can't believe we've attempted this so many times. But yeah, so we're going to take the rewrite, though. So we have a rewrite, so let's go take this. And we have like a one-liner, or not a one-liner, but we have a simplified version of the function where everything is kind of condensed, right? So we're going to take it all, and rather than calling this function twice, right, we could call this function twice, but we want to just make a consolidated place where we don't have to look at all that mental indirection, right? We can just use this, and it'll just work, right? So this is the input, right? So this is, the input value. So this is SX0. So we could just, this is going to be, this is the output. .x. So IVEC2 DST. Output. Okay. This is the destination. And we just want to hit all the inputs, right? So we want to look at all the X things. So here, this is X, this is X, this is X, this is X, and this is X. We only want to look at these. And so we know that this is SX, so we got that taken care of. So let's highlight that. S1 and S0. Well, we got SX0 and we got SX0. So that's pretty easy. Oh, DX0 and DX1? Oh, that's interesting. Bam. Right? So... So we'll kind of shorten this up a bit so that we can get it, you know, compactly thrown into here. And then let's clean that up a bit. And then all we should need to do is change the x's to y's, right? So we got this. This looks pretty good. We should just be able to take this, paste that, and we're going to change x's to y's, and hopefully that'll all work out for us, right? So x's to y's. So anywhere we see an x, we're just going to change it to a y. So y, y, okay. And then we just got to return that. So return DST. Okay, so this is our rewrite, much more concise, and I think the formula is actually correct, and we actually want to use this for a snippet now that we have, like, the correct logic, right? So this mapping doesn't use any floating point stuff, right? This will truncate, I believe, automatically, and we're getting the results we want, so let's make sure this compiles, right? We're gonna make sure it compiles, and then once it compiles, we're gonna throw it into the other test code, right? So we have this function over here, right? We want to throw the code into here once we got it working. So unknown escape sequence. So that's kind of scary. Okay. So somewhere in where we rewrote this, we're getting an unknown escape sequence. So I know sometimes it happens when in a multi-line comment. I don't know if that's the case, though. We're just gonna have to keep on trying to compile. We got a \t, so somewhere it's saying we have a \t. I don't know where that would have came from. Okay, so now I'm scared. I don't know where that's coming from. It seems like it's saying cc1.exe error unknown escape sequence. I have no clue where that's coming from. So I guess what we could do is, God damn it. Let's, try to... We only edited this, right? This is part of what we edited. So, it could be this. So we know that this is the thing that's getting wrapped. We know this thing is the thing that's getting wrapped, so I kind of think that if it is failing, it's because it's failing over there. Because it's wrapping that in a big string, and... Oh, we were over here writing comments, weren't we? Do we have a comment character somewhere in here? No. Oh, wait. \T, right here. That's where it's coming from. Because it's being wrapped in a string. There's that T. Yeah, there's the \. I did a /T, that's why I couldn't find it. Okay, let's steal this. Let's put this back. So halfway left side fail, huh? That's because we changed this function, but we actually were testing it in some places. So let's go look at that and see if maybe, perhaps this code is... So this is failing us. Okay. Well, let's make sure that we, let's make sure that we can see if, this code... Will this code also fail us, right? So does this rewrite... Did we rewrite it wrong? And somehow it's just not working at all, right? So let's make sure that we can pass these tests. Well, ST2 is failing us, right? So ST2 is failing us, and this is in, this is what, SC5? So we want to really concentrate on SC5 right now, right? So we want to not worry about SC2 right now. So let's comment these out. Because I just want to worry about, hey, how about, because maybe my test case isn't quite correct. Maybe I'm wrong, because I mean, we wrote a whole bunch of test cases, and we got more correct code for other stuff. So which one is this? This is our big test, huh? Oh, because we didn't comment that one out yet. So it seems like it's working, but it's failing here. And so what do we get? Like, test index number test index number 7 is failing us. And let's look at test index number 7. What is that? We're going from... So we're saying... It's not correctly remapping, right? It's saying, hey, 0 on here, and then we have this new range, 511, 511, right? And that's failing us. So what the heck is wrong with our formula that would make it kind of fail? Hello, how's it going?
Gramps is ordering steak at 5:30.
Okay. Okay. Thank you.
See you.
So what are we doing wrong here? I mean... Did we forget to add the range back on? This actually does look like it's not zeroed out, right? So this thing here... Yeah, this range formula doesn't account for origins, does it? Or does it? I don't know. I don't think it does. I think we screwed that up. Yeah, because right here when we call this function here, we made sure to add the new range on here, right? So we forgot that. So like after we do this, we have to remember to add the new low bound, right? So we got to add the new origin. And then over here, right, so we have the source calculations. We zeroed out with the origin here. Yeah, so we got to add the new origin. So destination x0, destination y0, it's those minimum values. We got to add those new origins. And if we do that, I think more of these tests are going to pass. Okay, so now we're failing on test index number 10. Let's go look in here. So we're getting 333, and we're expecting... Oh, we're expecting 333, 444, and we're getting 444, 555. So let's look at test index number 10 and see what we think about that. Okay, so test index number 10. We're expecting 333,444, but we're getting... So how do we even know that's correct, though? If this is the range here, to this range here... Oh, we're saying that if this is the first thing in this range here, right? And this is the first thing in this range... Oh, I see. So this is the lower bound, here's the upper bound, right? And here's the lower bound, here's the upper bound. Hold on. We just wrote that wrong, right? So lower bound, upper bound, xy, xy, right? So if that's the case, this is the lower bound, this is the upper bound. Lower, upper bound. Lower bound, upper bound, therefore we're expecting this to also map to wait, hold on. Lower bound and upper bound is one. So the sources, the source ranges. So first of all, we can see here we're doing lower, lower, upper, upper. Lower, lower, upper, upper, right? Okay. Then over here in test number 10, let's look at that. I know we screwed some stuff up. So test number 10 here. Here's the lower x's and upper x's. Lower x's and upper x's, okay? Or lower input, right? The lower input and the upper input. So supposedly we're off by... Okay, so it's the same test, it's the same kind of test. It's just... So the x is going to be between 1 and 2 here, right? So it's in the min. And then we want to map it to 3 and 4. Okay. And then the 2, well, we're between 1, the 2, we're between 1 and 2. We're between 1 and 2. The 2 right here, We're actually between 1 and 2, right? The lower bound and the upper bound, we're between 1 and 2. We're going to map it to 3 and 4. So we are in the upper bounds, and that's why we have the 4, 4, 4. Right? Or we just don't understand what we're doing, right? Because we're thinking that stretches, that stretches. I don't think it actually does. I think that we don't understand what this test is actually about. Because we think we're doing like a percentage thing here, and we're not. Right? So if we have like a no, that makes sense. So let's go in here for a second, and let's add more test code to, like... So we know that in our little test runner, we kind of use this here, right? This is the function we're using. And my question is... Right, we have this thing that's more correct. Or we think this is more correct because we're actually getting good results with this. Right? So I think, like if we take this, right? This is what we're actually using to render with, right? Yeah, this is the thing we're using to render with. And it's giving us some good results. So what I think is that we want to do... we want to do like SX, SY. Then I'm going to do SX0, SY0, SX1, SY1. They want to do DX0, DY0, DX1, DY1, right? We want to make sure that all these match, right? So, bam, 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 bam. So, that looks to me that we have copied that correctly. And let's test this new function first, right? So let's take this, and say, if, 1 equals the meta group for the test, then we're going to do this thing. And then else, if 2 equals the meta group for the tests, we're going to do this other thing, right? And we're thinking that this first thing might actually work, and there's something wrong with this, right? That's the idea. Now, we could be wrong, but let's just go with that. And so next, metagroup and test index. And then up here, let's just retrofit this, right? So for the metagroup equals 1, and the metagroup is less than or equal to 2, right? There's 2 groups here. And then metagroup plus plus. And then, did we declare this like way at the top? Is that what we did? Yes. Meta group / mega group of tests. Okay, so let's just give that a shot. And if we're going to use this, though, we need to make sure that we print off the actual test index that's failing. So So the meta group. Okay, yeah, so let's give that a shot. And then it's like 5, 6, 7, so I want to try to make something for MakerWorks really quick with my time that is left so far, if I can. Expected token. $10.59. In 10.59. Oh, because we have this. Yeah, we need 2 of these. Okay. So we're still getting this problem where we got this range 1 to 2, and then the output is 3 to 4. We're saying, okay, well, if you use 1 to 2, 1, 2, then it's, this is our mins to max, these mins to max, then we're expecting that we're going to have, you know, the correct min to max, right? We're going to have the 3, 4, but instead we're getting 4 and 5. No clue why that's working that way. That makes no sense. I don't know what's going on. Yeah, I don't know what's going on. I'm gonna stop the stream for now.